that, should I start again?
How much have you?
Oh, a few minutes, right?
No, that's my fault. Let us go ahead. Sorry.
Okay. And so we believe that in many situations, we're actually simulating these things fairly accurately. And yet, when you look at it, there's no, and all the atomic trajectories are, all the atomic trajectories are continuous, everything's evolving in continuous time. And so it's very difficult to reconcile our daily experience of what it means to boil water or to melt ice, and these kinds of simulations that we're running in order to understand this phenomenon. And if you happen to be interested in this sort of thing, these molecular dynamics simulations, and actually let me pop back over to the talk. Right, so these are known as molecular dynamics simulations. And I want to emphasize that molecular dynamics is one of the standard tools in the physical sciences. Just about any physics department, chemistry department, material science department of a revealed size will have a handful of people running these simulations. And I mean, every department at every university in the world. This is so ubiquitous. Typical simulations, right? So these simulations, they typically go from 10,000 atoms, if I'm simulating something very small on my computer, and I want to do this in half an hour, to hundreds of millions of atoms on some of the largest supercomputers in the world, right? So I work down the road at UC Davis from Lawrence Livermore National Lab. So they have one of the top 10 fastest computers in the world, and one of the reasons they have it is because they run these simulations. And so then you need to think about what are we doing here, right? So we've got some domain in R3, right? Because atoms move around in R3, you and I move around in R3, so atoms do that too. And so I'm going to talk about that domain as E. Typically, this is a torus. It's a flat torus, right? So it's a box with periodic boundary conditions. It's the only way we pick this. And I'm going to talk about the atomic configuration as being X, capital X. So it's going to be the set of all my atomic coordinates, right? The triplets, the X, Y, and Z coordinates of the atoms that are inside the domain. And I'm going to talk about the locations of each atom as value X. So, right, so these simulations, and so you're seeing here, this is actually a molecular dynamics simulation of what's called nanoporous gold. To give you some idea about this, an atom, the diameter of an atom, we don't actually think about these as point particles, right? They're represented as point particles in the code, but in practice, we think about them as little spheres, and we'll see why we think about them as little spheres. There's precise energetic reasons why that makes sense, but we think about them as little spheres about 1 angstrom of 1 angstrom radius, right? So 2 angstroms in diameter. So that's 2 times 10 to the negative 10 meters. So to give you a sense of the scale, right? So this is 5 nanometers. And so we've got, if I take atoms and I lay them in the end, that means I have about 5 atoms per nanometer. And so that this bar here is about 25 atoms if I lay them side by side, right? And so this is a kind of typical length scale. So these simulations, right, these might contain between 10,000 and 100 million atoms, and you might run this for 10,000 time steps, up to a few million time steps. So really tremendous clouds of data. My contention, we have no idea what to do with it. So part of this talk is a plea for help, because we need better ways of analyzing this data. And so I'm going to show you one way that I've been trying to attack this problem from the standpoint of phase transition. So it's a very specific type of problem. There's other types of problems that people look at in these point clouds. But if any of you are hunting around for dynamic point clouds, there are almost certainly people at your university who can generate this. Great. So the dynamics, where do the dynamics come from? So we have these points, and I'm really remember, right? They're all wiggling. So it comes from this potential energy function, right? And so one of the things I want to do with this talk is I want to give you language that we use in physical sciences. So when you go and you ask a physicist for something like this, right? You can talk to them using words that they understand, because they're simple. Right. So we have a potential energy function U, and so what this is, it's a scalar function. It goes from the atomic configuration into reals. We talk about the scalar values of potential energy. And if we take the gradient of this function, right, the gradient of the potential energy, that's going to describe the forces that are in each one of the atoms. And then we integrate Newton's equations of motion, and all the atoms move around in the way that do. And so what that means is that all the physics in the simulation is encoded inside this function, inside the scalar function. The scalar function, along with the initial conditions, completely determines the deterministic evolution of this system. It is completely deterministic, right? Okay, so this is something that I have to talk about with all of my students who end up using these kinds of things. The physical insight doesn't come from the atomic configurations. That's not. So this is nothing new to all of you who do topological data analysis. You all know that. But the kind of prototypical example is you can do a rough calculation. You take, say, a household animal. You know the volume of the animal approximately. You know the volume of an atom. So on average, there's around 10 to 26 atoms in a typical household pet. So I now do the following thing. I write down the atomic species and the positions of each atom in a household pet, and I provide you with that list of 4 times 10 to the 26 numbers, and you tell me the sound of the animals, right? So obviously this is impossible. And so what we need to do is we need to go from this set of atomic configurations, right? So from the set of atomic coordinates into something which is useful, right? Is this in liquid? Is this in solid, right? So, and that actually is non-trivial. So one way that people have approached this is actually a paper by Yasu back in 2016. So PNAS is one of the leading journals in the physical sciences. And what he did was not very, it's not very sophisticated from the standpoint of topological data analysis. What he did is he took that point cloud that I showed you, and he looked at the persistence, right? So you take each one of those atoms, you inflate a little bit, and you ask what kind of cycles appear and when they appear and die. And you get 2 different kinds of structures. And so this was the case roughly corresponding to a crystalline structure. It's actually a crystalline structure that's perturbed a little bit, so the atoms are wiggling around just a little, like at the beginning of the simulation. And if you do that, you see these clusters of features, which corresponds to, and you can actually identify these as triangles of different shapes. And so this is when we're looking at 1 cycles and 2 cycles, right? And again, you can identify these with tetrahedra or octahedra and things like that. And so depending on the crystal structure that you're working with, you're going to see different kinds of clusters. You can identify those with different features of the crystalline lattice. Now, if you take the water at the end, which is an amorphous structure, you see things like this. And that makes sense, right? It looks like a pseudo-random distribution of points. It's not, it actually has more structure. But if you think now about the simulation that we saw at the beginning, what's going to happen is you're going to go from these into these, and it's going to happen continuously. Yes, right.
So in the left picture, why is this not sort of connected? Because the triangles might change their shape. On the top right, I do understand that you might have different isolated patches because they have a different combinatorics. But if you have 2 triangles, shouldn't it be connected?
So they might be, but in the case of a crystal lattice, the translational symmetry of the crystal lattice is actually extremely rigid. And so you don't end up having a continuum of these angles. You have very well-defined angles. And in this case, you do have some variation because there was some temperature. So it's very, very slight. But yeah, but it's actually, I don't know if someone has sat down and studied this extensively. If I hand you one of these persistence diagrams and you tell me conclusively which crystal it came from, I don't know if that's been studied. But each one will presumably have a different signature. Right, so this is the way that Yasu approached it. And this worked very well for identifying the kind of thing that you're looking at. I claim it does not work that well predicting when this will happen. So predicting the temperature at which water ice melts, right? And in fact, I'm interested in predictive power because I want to be able to run these simulations for materials that we have not fabricated yet. And I want to be able to make predictions about how that will behave after we form it at the lab. Yes? For what claim? So, so you can recognize the phase transition with these, right? So that's, that's the claim. one of the things I'm interested in is being able to predict where this will be without running the simulation, and then running the simulation after the fact to check. Right? I want an independent verification. I want to use it in that way. You can also use these MD simulations for data exploration, and people do this all the time. Right? In fact, that's the standard approach. Great. So, the first thing that I'm going to claim that we want to do is we want to move away from R3. Okay. So, there's nothing too surprising here. What we have is capital X, so that's giving us our triples of all the quantum coordinates. And I claim that all those points, they are going to sit in some space gamma, which I'm going to talk about as the configuration space. So a point in this configuration space completely defines your atomic configuration. Okay, great. And so to help the visualization, right, so here's a very simple example. So it's a one-dimensional molecular dynamics simulation, and I put down 2 atoms. And so here's your configuration space. And this is not quite right, but I didn't feel like I didn't figure. But so you're supposed to look across here and then see off left where atom 1 is, and you look on the vertical axis where atom 2 is, and so this roughly corresponds to that point. You notice I've taken out the diagonal because we require that the points don't overlap. Right? We don't allow atomic fusion. That is not a thing that we're simulating. So I said that all the physics is contained in this potential energy function. We don't actually write them down like this. So very often you want these things to be analytic because we're taking derivatives. We want the derivatives to be fast because we need to be able to do this with forces. The earliest simulations used these what are called parapotentials. And so this is a function between 2 atoms. It's based on the isotropy and the homogeneity of space. It can depend only on the separation between the atoms. It can't depend on the direction. And so this is just the magnitude of the difference. And what I've done here is I've just taken some overall pairs. Right? So these kind of parapotential forms were very common on. We realized pretty quickly that we can't reproduce useful simulations of actual materials using just parapotentials. So effectively, all materials use multi-body interactions of various types, right? So the multi-body interactions you see in carbon are completely different from the ones that you see in copper. And so we've actually, the field has kind of, it's not bifurcated, it's actually split up into many, many more pieces than that, where each discipline that's studying a particular material class will develop different interatomic potentials to suit their materials. But this is kind of the basic form. So the typical, but all of these typically have a parapotential component. So these functions typically look like this. So we know that this should decay as about 1 over r to the 6, right? So it decays pretty fast. What I've done here is I've constructed this function so that along the horizontal axis, we're looking at it in units of the minimum energy separation. And so you'll notice that in fact it goes to 0 pretty fast. So it's a very short range interaction. And this is again typical of most atomic systems. There are examples where this is not true, but that's not so many. You'll also notice that it goes up to infinity quite quickly. So this goes approximately as 1 over r to the 10, or 11, or 12. We're not really sure. It doesn't really matter. They don't overlap, right? That's the thing that you should take away from this. And so now U defines a function. It's a scalar function on our configuration space. And so if I take this and I evaluate that, I can plot this for you here. So this blue is 0. The darker blue is the region where the energy is a little bit lower. So atoms act a little bit like sticky spheres. They like to stick together a little bit. But if you try to push them together any more than that, the energy becomes very large, very, very quickly. It becomes so large that if I was to plot this whole thing on scale, you wouldn't actually see this little sticky ridge, right? So I didn't do that. I just omitted it completely. So now you see that there's this band of extraordinarily high energy right here on the diagonal of my configuration space because the atoms don't want to touch each other. Okay. Right, and so I said this before that U completely, along with the initial conditions, completely specifies the trajectory of my atomic configuration. So this again is a completely deterministic system, which is a little bit of a lie because we do all kinds of things to make it non-deterministic, but in principle, right, in the simplest case, that it's deterministic. So what happens? So if you've got this kind of trajectory, right, you might start out at some initial configuration, and then I have to pick some initial velocities for my atoms, and then get the simulation up and running, and you might see it bounce around like this. And so what's happening here is it's basically the atoms are just bouncing off of, in this case, they're bouncing off each other. But remember, there's a very strong repulsive interaction when they get close, and so they bounce off. And then this atom is bouncing off the side of the simulation domain. And so these things are just going to bounce around, and they're going to trace out some kind of trajectory in space, right? And so this is, again, the reason I picked this is because I can actually draw this configuration for you, right? Because typically, if we have n atoms, this is going to be 3n dimensional. And so you'll see something like this. And the idea is that this atomic trajectory is going to be exploring this bit of space, okay? And so here's now the step where we start moving a little bit away from molecular dynamics simulations, and we start saying, well, how can we predict what these are going to be showing us? And so this now enters the realm of what's called statistical mechanics. And statistical mechanics is both one of, in my opinion, one of the cornerstones of modern physics, and one of the most beautiful pieces of modern physics. And it's also one of the pieces that is in sorest need of deeper exploration of the theoretical foundation. So you may hear people talk about this. This is going to be an introduction to in one slide. So the idea here, there's a couple of other basic ideas. One is the ergodic hypothesis. So the ergodic hypothesis says that if what you did is you watch the evolution of the system, right, and then the waterfall. So you go and get your key, and you come back and you look where it is, and then there's a phone call, and you come back and look what it is, and so you're sampling the locations of this system in the configuration space at the time, and you assume that these interruptions are long enough that it's effectively uncorrelated, that you're going to be sampling configurations according to some probability distribution P on your configuration space of points, gamma. This distribution, right? So this is actually a probability measure, which is why we have this proportional. This probability measure is known as the Gibbs measure. It is believed, but not proven, to be the unique stationary measure on the space defined by these dynamics. It's not proven. But you'll notice that this energy appears very prominently here. So it's an exponential of negative the energy divided by a constant times temperature. The consequence that up here is constant. The probability gets a little bit higher, where my energy is a little bit lower, and then it drops off to zero, because these spheres are strongly repulsing. Right. So the ergodic hypothesis says, among other things, right? So not only is the probability of a particle distributed according to this probability measure, but also that the particle, the system will explore the whole configuration space, right? Because you notice that I have non-zero probability down here also. Okay. So then you tell me, well, that doesn't make any sense. You just showed me a trajectory in the previous slide, but I didn't have it. Right? On the previous slide, we had a trajectory that was bouncing around up here. So why is there probability mass down here? This is absolute nonsense. And so, most physicists, and I've spoken to them about this, they get a little bit uncomfortable. And then if they think about it, this is often the response. That, right? So, well, what you really meant to do is you forgot that we have this isometry sheet. And so in this case, for example, we might have the action of the symmetric group on these two atoms because atoms are indistinguishable. So if you swap the two atoms, you have no idea that I did that. It looks exactly the same. All physical properties are identical. And so what that means roughly is that I need to look at the quotient space where I've identified points across the diagonal, right? And so that's how I fix this up. So there is only one connected component after I've modded out by the action of this group symmetry. Okay. Now, how do we identify things like phase transition in this framework? So the way we do that is we put on these scalar test functions. So we're going to put a scalar function onto the space. It's going to be known as an order parameter. The typical way that we talk about this is this little tornado sign, I guess. But tornado. And so it's a scalar function defined on the space. It has this property that is constant on the orbits of G, right? Because physically indistinguishable configurations should have the same value for this order parameter. So now here's the fundamental postulate, right? There's two essential things that you need to remember about statistical mechanics. If you ever talk to me about this. So one is this assumption of ergodicity, right? That the probability distribution of states is distributed in this way, according to this Gibbs measure. The other fundamental idea is that I can connect what we're doing on this configuration space by taking these averages. But the time average property right? If I look at the value of xi along my trajectory, and I take the time average, I will get out an identical number if I take this average, this expectation value, over my entire configuration space. That is the fundamental postulate. It's an axiomatic, right? So, so then how do we identify in phase? Well, we're using these test functions. We're using these scalar functions in order to identify when there's a phase transition. So how does that work? Well, traditionally, and actually this continues in modern practice, if you go into a laboratory where people measure these kinds of things, what we find is that if you are sensible about picking the order parameters, because not just any order parameter will do, the constant function obviously is not going to be sufficient. So if you're sensible about picking these order parameters, then what happens is this expectation value exhibits a discontinuity. It discontinuously changes as a function of some independent variable. So if I've got my temperature, so this is actually my paraffin wax, as I'm heating up my paraffin wax, this is the energy per atom. Don't worry about the fact that it's an enthalpy. It's effectively the same. So the energy per atom is going to increase, and then we have this discontinuous jump. It's supposed to be discontinuous. The reason it's not is because we have finite resolution in the lab. Right? So there's some experimental error. But this is supposed to be discontinuous, and then it continues on the other side. So that should be kind of surprising, right? Discontinuity. It makes sense in terms of the properties of water vapor and liquid water, right? So there's no surprise there. But where's the discontinuity come from? Because again, our probability measure is continuous on the space. And my order parameter, I'm assuming that it's smooth. So where does it come from, right? So I just assume that the order parameter is smooth and supports P. So again, if you ask this to some physicists, then you get a little bit comfortable, and then if you think about it a little bit, then you might say something like this. So maybe the domain of integration is actually what's changing discontinuously, right? So maybe the ergodic hypothesis was a little bit too strong. And in fact, the particle doesn't explore the system doesn't explore the whole configuration space. It just explores the connected component that it starts in. And when it has enough energy to actually start exploring other pieces, then my domain of integration in these expectation values changes. And if my domain of integration changes discontinuously, then the value could change discontinuously, right? And so the idea with this is, suppose that I've got, this is the first time topology comes in, right? And it's not even really topology, it's just an awful complex. But suppose I've got some point cloud, and what I'm doing is I've got energy values on the vertical axis providing filtration. And I start constructing my alpha complex according to this. You're going to see things like this. And so if my atomic system starts down here, it can be exploring this domain. And so I'm performing these expectation value averages over this region until the energy gets high enough when it can get over this energy barrier and start exploring this piece. And so now my domain of integration has changed discontinuously. And so this allows us to have a possibility of a phase transition, right? Okay, so how do we test that? Well, I guess what I need to do is I need to look at the topology of the accessible regions of the configuration space, right? How are we going to handle this? Well, we're going to try to simplify things, right? We're going to try to boil this down into a model problem, to a well-defined problem that we can talk about in precise terms. And so the first thing that I'm going to do is I'm going to say, well, this little sticky bit, it's hard to deal with. So some people have done this, like Miranda Holmes, who's done some very interesting work on configuration spaces of sticky spheres. But we're going to try to simplify this by replacing the atoms with hard disks, right? So there's balls and they do not overlap. So the way that you can represent that is by changing this pairwise interaction potential to be one that just diverges to infinity at some cutoff. And I'm going to talk about this cutoff, this point at which this happens as rho, but it's going to be the radius of my disks over here, okay? So we've got this kind of one parameter family of pairwise potentials. What that does is it changes my potential energy function to be identical to 0 in the allowed region and infinity in the disallowed region. And so that changes my probability measure to be 1 out here and 0 in here, right? And so you see that this is not a huge change, but it makes things a lot simpler because, now it's just constant out here. And so the only thing I have to keep track of is not really the value of my probability, my probability at each point in the configuration space. I just have to know this domain because I know that my probability is constant on that domain. Okay. So how is that domain defined? Well, I claim that there's a natural filtration on this space, and it's given by a function known as the topological function tau. And so this notation, and actually the name of the topological function, I believe, was proposed by Matt Kale in conjunction with co-authors. So the idea of the tautological function is you've got some point in your configuration space, and you're now interested in, so that point in the configuration space defines the centers of the disk, and I'm now interested in how big I can make the disks without them overlapping, right? And so tau quantifies that. So if I have a point in my configuration space out here, you see that the value of the tautological function is quite high. That means that I could, in principle, put down very, very large disks with the atomic centers in these positions without them overlapping. And as I move the point around in the space, so I go to lower values of the tautological function, you see that I'm still in the allowed region because my disks are still not overlapping. Indeed, I could put bigger disks down, but not quite as big as when I started. And that's why the tautological function value has gone down. And so forth, right? So I get lower values. I'm getting close to the boundary, this kind of cutoff that I've defined. And again, this is allowed, but I can't only increase the radius of my disk to a very small amount, and so forth, right? And so what this does now is it says, it gives us a kind of natural definition for what this region is going to be. So we can define that in the following way. So we have this tautological function tau. It's a min type function, right? So tau is actually a minimum of the pairwise separations of every pair of disks. So it's smooth in many places, it's flat. You know, the derivative is constant on some kind of some areas, and then it's non-differentiable in others, where we switch from one piece of the minimum to the next, right? So it's not a Morse function in the classical sense, right? It's non-differentiable, but it is a function from my configuration space of points and reals. And what I'm going to do is I'm going to define my configuration space of hard disks of radius rho as the superlevel sets of this function, right? Because I could put in disks of radius rho or bigger ones. And so that seems like that's just fine if my disks are only of radius rho. I definitely can't put in, I don't have configurations where the disks are overlap. So this is how we define our configuration space of hard disks. And so now the physicist in the room who's losing patience says, well, what does this have to do with phase transitions? You said there were going to be phase transitions. And then I say, okay, well, there's this paper. So this is by Hannah Alpert and Matt Kale and Bob Pearson. And it was published very recently, I think in the last year. They finally finished it because there was some very delicate stuff that they were doing. But the idea with this is that we have an infinite strip, an infinite channel, and I put down a bunch of disks, hard disks, can't overlap. And I have got some questions here, right? So one of the things I can do is I can fix the number of disks. In this case, I can just fix it from 3. And I'm interested in the width of the channel as a function of disk diameters, right? So we use disk diameter. And what they're doing is they're looking at the jth homology group, or the jth Betty number, on the vertical axis. So these are the Betty numbers, and the width of the channel. And I believe that Bob McPherson actually sat down and dreamed up a cell decomposition one day, and they spent a number of years trying to work out exactly what that implied about the Betty numbers, but here it is. And so you'll notice a bunch of interesting things that happen. So if I've got a bunch of disks and my channel is small enough, nothing happens. No disks can move past each other. All my homology is trivial, right? That makes sense. If I make my strip big enough, I get a configuration space of points, and the homology of that is known exactly, right? And so out here, my Betty numbers, they go, if n is the number of disks, these are just powers of n, right? So n to 2, n to 3, n to 2, n to 4, n to 6, and so forth. Now, what was really interesting to them, and was really interesting to me, is that there's this little region in between where the homology is wild. It's exponential, right? So you see things in here like 3 to the n cubed. And I'm not sure that's a cubed because I don't have my glasses on. But the homology is very, very complex, right? The topology of the space is extremely complex in this intermediate region, right next to the region where it's trivial. And so what that means is that as you're increasing the width of this channel, there is this wild change from no homology to exponential Betty numbers. And it's completely discontinuous. So by the way, one of the reasons why you might think that you can actually do this is because all your cycles are going to be embedded tori, right? And so here's a particular configuration for one of the embedded tori. It's a very nice paper, actually. It's right down here. So here's something that comes from kind of experimental physics or material science, depending on what variation of scientist you call yourself that day. So we've got the volume of our system on the horizontal axis, temperature on the vertical axis. This works for water, it works for copper, it works for basically any system that melts, which is most of them. And so when the volume is very small, you're stuck in solid. Why are you stuck in solid? Because the atoms don't have enough volume to move past each other. They're just locked into position, whatever position they started in. So you're in a solid over here. And that if you make the volume large enough, you end up in the gas phase, right? Because there's a little bit of subtlety. This is a great simplified diagram. You have to be at high enough temperatures and high enough volumes to get into the gas phase. So that water that's in your kettle, you have to raise the temperature high enough and give it enough volume to expand, and then it turns into gas. And again, there's a little bit more subtlety because you do have a liquid here, the pure gas is over here. And you've got these, we technically call these two-phase domains where it's all solid here, it's all liquid here, and here it's a mix of the two. And there's various reasons why that is. But you'll notice the similarity, right? So in the solid, all the atoms are stuck in place. They don't have any room to move. That sounds a lot like trivial homology. Now here in the gas, all the atoms are well separated, and I can treat them as points. That sounds an awful lot like this homology of points, configuration space of points. And so then I have this liquid, and by process of elimination, it looks like the homology is wild. And that kind of makes sense, because in the liquid, the particles definitely feel each other, and they feel obstructions from each other. But when you pour water into your cup, it takes the shape of the cup. And so they're able to kind of roll around each other. And so this feels very sensible. And so then you might look at this, and if you're like me, you might say, well, maybe that means that there's going to be a topological signature in the configuration space as I go from here to here. Let me try to figure that out. Right. So yes. Yeah. The width of the channel in units of discontinuous. So that's why it's naturally matched to the volume of the system. So this brings us to the topological hypothesis, which is known to be false. So Francesco was actually, he was on a paper with Franzosi and Pettini, who originally proposed this and then eventually said that this is a theorem that they proved, which was disproved by counterexample from Passer and Metta. Francesco, I mean, the paper that he was on was actually, I mean, completely different, right? But he was on another paper with the same co-authors. But the idea with the topological hypothesis. Should I switch it? My cell phone, let me turn my cell phone on. Okay, great. So the topological hypothesis says that the appearance of critical points of, say, the tautological function, or it turns out equivalently the potential energy, and I'll tell you why that I think that those are the same, the critical points, we can identify them, are intimately related to the appearance of phase transition. And in particular, there's some topological catastrophe that takes place. And this topological catastrophe is really what drives it. So that's the topological hypothesis. And as I said, we have a counterexample, and there's some technical stuff that happens there. I don't really want to discuss it in great detail. The original papers describing the topological hypothesis are virtually impenetrable. So we can have a longer discussion about it, but I don't want to go into details here because I'm focused on trying to give you the higher level ideas. Great. So what might we do? Well, if we have a space and we've got a natural Morse function that we can use, we might look for the critical points and look at the distribution of those critical points. Our natural function, I claim, since we've passed to the hard disk system, is tau, and it's not differentiable. So what do? Well, so this was a result by Baryshnikov, Bubenik, and Kale back in 2014. And what they started to do is they were thinking about precisely these problems. This might have been the same paper where they actually defined this topological function tau. They said that, well, if you've got this kind of min-type function, it has a min-type function, then the critical points of that are defined in the sense of attaching handle bodies, right? So I know that I attach a handle body when I pass from this value to this value, and I have such and such critical point in the middle, are mechanically balanced configurations. So what are mechanically balanced configurations? These are them, right? And actually we have about 1 million, give or take a factor of 2 of these kinds of points for various numbers of hard disks. If you're interested in these, we've got them publicly available. I would love somebody to use this data because we spent years collecting this data and we just don't know what to do with it. So if you want to, we can take a look at these. But so these are the kinds of configurations. I think this is for, I don't remember, maybe for 12 disks, 12 disks. And these are actually in the hexagonal course. So when I say mechanically balanced, I mean the following thing. You've got these configurations. You have contact graphs. I'm showing you contact graphs. And the idea with mechanically balanced is that I cannot, remember the disks are not allowed to overlap. I cannot increase the radius of the disks by any motion to first order, right? Reverse those. I cannot increase the radius of the disks to first order by any motion. I can increase them by second order. And in fact, the number of independent motions by which I can increase the radius of the disks to second order defines the critical index, right? So that's how it's defined. But mechanically balanced means that if you just had these disks and you tried to inflate them, you would not be able to. Yes?
Maybe a stupid question, but what does it mean to increase the radius to first or second order?
Right. So I've got a rate at which I'm increasing. I've got right. So I've got a point on my configuration space of disks.
Okay.
Yeah. And now I can think about changing this configuration. And so that's going to give me a path in my configuration space of disks. Parameterize that path by arc length, by path length. Okay. And so now, if you try that, I claim that there is no path such that the radius of the disks increases along that path to first order in your arc length.
So any increased room cannot be linear in my.
That's right.
But it can be quadratic.
It can be quadratic, and in fact, the number, and you can do similar kinds of things with the Hessian and eigenvalue analysis, and you can work out numbers of linearly independent directions to which increases second order. But you should think about it in the same way that we think about classical mass theory. But yes, yeah. So that's the condition. So.
This is the meaning of mechanically balanced configuration.
So Baryshnikov-Bubinick and Kale give a slightly different and more technical version, right? So if you really want, you can go take a look at that. But the idea with this is an equivalent way of thinking about it, which is that I can put forces. I can think about each one of those edges as being repulsive springs. And if I put forces on them in an appropriate setting, and the forces are non-zero, there exists combinations of forces I can put down such that no disks move. Right, this is an equivalent definition, and again, they give a slightly different one.
Why these are related to the critical points, or why critical points are just related to this configuration?
That is a question I would like to discuss with you in more detail after the talk, because there's certain technical things there, and I spent so much time preparing so many pictures. I really want to show you the pictures before my talk is over. So, okay, are we good on the slide for now? Okay, great. So how do we find these? So this is how we find them. This is a simulation that we actually run. And as I said, we found 500,000 of these. We found them both for hard disks and for hard spheres, right? So we've mentioned. And so the idea with this is that if this was a classical Morse function, what we would want to do is we would want to find the gradient. We'd want to find the magnitude of the gradient, and the magnitude of the gradient. This is now a scalar function on my configuration space. And so what I can do is I can just start with an initial point, and I can do gradient descent, and I'll find some minimum, some local minimum where my gradient is 0, and then bam, that's a critical point. Except this is not differentiable. So we do the following trick, right? So we realize that this topological function, we have a minimum of the radius of the disks that, this is actually half the pairwise separation of two disks. That's how we define R. Rho is going to be this scalar, which is the radius of the disks for my particular configuration space. So this is just, I think in the definition of tau, that's subtractive rho, so nothing special there. This is known as a soft min approximation. So what this does is I've now looked, I have these exponential functions. I have one for each pair of disks. So the pair of disks with the smallest separation is going to be exponentially larger. It's going to have an exponentially larger contribution to something than anything else. The logarithm kills everything except for the largest one. And so this acts like a min. It's an approximate thing, but it becomes exact in the limit that W goes to infinity, right? Because what that does is it just emphasizes the exponential where my separation is smallest more and more. And so then what I do is I notice that this subtraction is a monotone operation, obviously. Multiplication by a constant is a monotone operation. The logarithm is a monotone operation. And any strictly monotone transformation preserves locations of my critical points. That's not a proof, that's my intuition. I have never found a counterexample. But again, like, you know, I'm not a mathematician, so it's not my business proving things. So I claim now that this function is going to have identical critical points to those of tau, which was not differentiable, right? But this is differentiable. And I can make sure that the critical points coincide, right? So I'm defining the critical points of tau as kind of the limit of some Cauchy sequence, right, of these as I'm increasing W, right? And so that's how I'm defining my critical points of tau. So if you don't like this idea of mechanically balanced, you can think about this and just crank up that parameter W, right? So this is actually how we do it. So we have this continuously, this is an entire function. And so all we're doing is I'm looking at the magnitude, the squared magnitude of this function, and then just doing gradient descent. And we start with lots and lots of initial configurations and just flow down and we get, you know, a few 100,000 of these things for different numbers of disks. And so this is what it looks like. Yes, it's off, right? The battery on this is almost dead, so maybe I'll have to switch mics again very soon. Right, so I just said this already, but if you go through this and you believe my reasoning, then the critical points of this should be the same as the critical points of tau. If you could define such critical points, we've talked about them as the limit of the sequence in the W goes to infinity limit. And you'll notice actually that in this kind of setup, rho is just a parameter that I use for numerical conditioning. Right? If I multiply every term in this by an exponent of negative W rho, it definitely doesn't change where my critical points are, right? It's just multiplication by a constant. And so in fact, I use rho in this sense, just for the numerical condition. The critical points, the location of the critical points is independent of that choice. Great, so let's do a little bit of example. So I'm actually going to talk to you about two different systems. So one is this the square torus, and then one is this hexagonal torus. Why am I looking at two? Because I'm interested, remember what we're interested in. We're trying to get at the topology of these spaces under the hypothesis that somehow the properties of that topology, we should have a topological catastrophe at roughly the same area fraction covered by the disks, independent of the choice of my boundary. That is something that needs to be tested. So we'll try this. I'm only going to consider two disks. I'm considering two disks because I can actually draw these configuration spaces for you. You will see pictures of these. And you say, well, that I don't believe you. You can't do that because each one of these has 2 degrees of freedom, and there's 2 disks, and so that means it's maybe a 4 manifold, maybe not a manifold, but locally 4-dimensional. And then I claim, well, actually, remember what I said about the group of isometries that you're supposed to mod out by. So the very first thing that we do is we mod out by translations of one of the disks. So we fix one of the disks, and that kills this. It makes these critical points isolated, right, which you can definitely want. And it puts us down on something that looks kind of like a 2-manifold most of the time. Okay, so these are what our critical points look like. So these are our index 0 and our index 1s, up to the kind of natural isometries associated with discrete symmetries of my fundamental domain. Okay, so the next thing we do, I want to make explicit triangulations, and so I'm going to put down a metric. Right, so this is a metric on my configuration space of points, and nothing very special here. It's just you give me a set of label points for configuration X and a set of label points for configuration Y, and I just figure out the sum of the geodesic distances I require to displace each point by. Right, so there's nothing very special there. Typically, though, right, we need to mod out by some group of isometries. I just told you that we have to mod out by translations, right? And so because we're only modding out by the action of isometry groups, it's almost a trivial proof that if this is a metric, then this is going to be a metric also, right? So you're just taking the infimum of these distances for all, in this case, translations of the disks. So you just move the disks around, you take the infimum, and then there you go, right? Because that defines a metric on your quotient space. And so what does this look like, right? So here, where I'm going to talk about now modding out by different kinds of groups and the actions that those have. So here's just our base space, and so I've got some yellow disks. So I've colored the disks by their labels, right? So I've got yellow disks and I've got green disks, and I have open ones in one of my configurations, and I have closed and shaded ones in the other. And so what you're seeing here is these displacements that I have to apply to my disks to go from one configuration to the next. So now if I mod out by translations, well, the effect that that has is that I'm basically taking the empty ones and allowing myself to translate these arbitrarily into space in order to minimize that sum, right? And if I also mod out by the action of the symmetric group, I can no longer distinguish the disk colors. And as you see, the displacements that I have to apply get a lot smaller because our space is getting smaller because we're modding out by more. And then if I also mod out, and I don't know the right notation for this, notation, so translations, and then this is the symmetric group, and then this is going to be my group of discrete symmetries associated with my fundamental domain. You actually, so this is in this case going to be rotations and mirror reflections, right, of this hexagon. The distances become a lot smaller, and so we can define metrics on all of these quotient spaces, right? Great. So here's what they look like. So if you take your configuration space of disks and you modify translations, you see these kinds of things. So I'm coloring these by the filtration given by the topological function. And you see a bunch of critical points. And so these are index 0 critical points. And then as you shrink the disks, right, these spaces expand and you have these long tendrils that kind of meet up. And so those are going to be our index 1s. And then it goes on. And technically, what you want to do is you want to work with the 1-point compactification of these. We don't actually include that, but that's where the 2 cell is supposed to be, right? It's missing because we're not doing the 1-point compactification. But again, don't worry about that. That's a subtlety. It's not so important. So then we start modding out by some symmetries, right? So I'm going to mod out by the symmetric group. And we actually, in this case of the hexagon, we had 2 critical points in the same equivalence class, but 2 critical points, and here they give just 1. And again, this thing expands. And now here is a critical point in both senses. So here we've actually got these two connected components, and then they merge up at these index 1 critical points. In this space, we don't. It's not a critical point. It's not connecting to anything, but it is a stratified space. It's not a manifold. It's not a manifold because these points out of the corners are singular. I showed this to Bob McPherson, and he was like, "Oh yeah, that's completely obvious." It's not obvious to me. And thinking about the action, what these quotient maps do to critical points in higher numbers of disks, he might already have a picture in his head, but I don't. So yeah. So if you modify the last group of isometries, this you think about this as being a group of order 12, I guess. And so you're going to have 1/12 here. So it's this little triangle, and this makes it even more clear, right? So we start out here, and we've got this isolated index 0 critical point, and then it expands out, and you can see this kind of singular configuration very, very clearly there, where it is no longer a manifold. It's a manifold most of the time, but just not there. Okay. So these are alpha complexes, incidentally. Great. So I want to show you some other stuff too. So let's talk about hard spheres, right? So remember where we're driving. I'm interested in the topology of these spaces. And the hypothesis is that this topological catastrophe, if it occurs, should occur in 2 dimensions and in 3 dimensions and for different kinds of domains. And so we're going to test a bunch of these. So here we go. So here is a Pentagonal Dihedron. This is the kind of prototypical cell that I'm going to be using in R3. It's a 3 torus, right? I've identified opposite sides. Great. So we've done this for between 1 sphere to 12 spheres. What you're seeing here are the densest index 0 configurations that we found. We don't know that this is not an enumeration, these are numerical techniques that we're using, but you see a bunch of common crystals types. So this is a simple cubic lattice. There's a BCC structure for a couple places in here, and there's some FCC structures and some that look kind of wild. We're not quite sure what those are, but the kinds of invariants of the crystal structures that we've been hearing about this week would be great to analyze these if anybody wants to apply that. Now I can do the same thing. I can take the configuration space of points in R3, right, and we can restrict it to hard spheres. And I'm going to put 2 hard spheres in, and then we're going to look at what the spaces look like as a function of this filtration value. There's 4 critical points incidentally. So this one is, so there's two hard spheres. This, I believe, and I might need to put on my glasses, but I believe that this one is a simple cubic or a diamond structure. Sorry, this is a diamond structure. This one has 2 different hexagonal. Maybe I'm getting this wrong. No, I think that's wrong. So this is I think a simple cubic. I should really put on my glasses. This is a diamond structure. This has 2 hexagonal sheets which are offset from each other, and then this is just them in lines, right? So this is index 0, index 1, and index 2, right? Because there's 2 linearly independent motions there allowing the radius of the spheres. And you see actually that this is isolated. We have another index 0 critical point because, and you'll notice this from the Pentagonal Dihedron, that there are 2 vertices of different types, right? So there's one type of vertex here, at the joining of 3 faces, and one at the joining of 4. And so you would naturally expect there to be 2 different index 0 critical points, and there are, and they appear at the 2 different types of vertices. And then our index 1 connects those up, and then our index 2 kind of fills in these spaces. And again, the 1-point compactification would correspond to a 3 cell that fills in the interior, but we're not worrying about compactifications. But then the same thing happens. So notice if I start modding out by the rest of these isometries, I go from this to this. So this is a little tetrahedron, and you see I've got 1 index 0 and 1 index 0. And I've got an index 1 that appears here. Now this is quite interesting, right? So this up here was an index 2, corresponding to pasting in the image of a disk. Here, nothing happens. I hit a corner. That's weird. Again, it's not obvious to me what these quotient maps are doing to the topology of the space. I can show you. It's not obvious to me until I saw that. Right, so the topology of the spaces changes differently. Which one is relevant to the topological hypothesis? And then the 6th one is a little bit of an interlude, and I'm just going to skip this. Right, so here's how we're going to try to test this, because I've got 5 minutes left. Frank, should I quit now? 5 minutes? 5 minutes, okay. So here's how I'm going to try to test this. So one of the ideas that we had is, well, maybe what's happening, because we have these kinds of singularities where we have these stratified spaces, right? And we don't have these critical points. Maybe the important thing is not actually the topology. Maybe the important thing is the geometry, because we have this singular geometry. So how do you test that? So one way that you could do that is you could test the space diameter. But it has to be a very particular notion of the space diameter. It's not just the 2 most distant points, because what we saw in that corner was, if I think about this, a point undergoing a random walk, it's long and singular. And so it's going to be extremely hard for it to get down that neck. So what we need is something that is related to how quickly the trajectory is able to explore the space. Right. So there's a couple ways that you can do this. So the one standard way is by diffusion distance. And so what the diffusion distance does is it puts down 2 Dirac delta measures and then just applies the diffusion equation and examines how close these distributions are as a function of time. Right. And so you can do that, and that's this dark curve. And what you see here, so these correspond to these different dashed lines. So here it's not connected, and then here it is connected, and you see this discontinuous jump in the diffusion distance, if that makes sense. But this is a little bit concerning, because there what happens, we went through this constriction, and we have this noise associated with the boundary of our alpha complex. And that noise associated with the boundary of the alpha complex caused us to have this jump, which is not physical. And so what we want to do is we want to define a different quantity, which is known as the mixing time. We talk about it as the epsilon mixing time. And so here's a blow up of this inset, and you see that it has a discontinuity at the place where it's supposed to, but it's smooth out here. And we basically do that by weighting this idea of diffusion distance over all possible locations of the points and taking kind of the expectation value for these things to line up. And again, right, so in the interest of time, I'm going to skip that. So here's how it works. Right? So what we have is I've got my configuration space of our disks and our spheres. And what we're doing here is we're looking at packing fractions. So you should think about the disk shrinking as I go in this direction. And what we find is that the diameter is pretty small because I'm stuck in my component until it connects up, and then I have this spike. And I see that, interestingly, no matter which isometry group I'm mod out by. That was not obvious, but it works. And we see that both in 2 dimensions and in 3 dimensions. So then what you do, and I know I'm coming up on the end, So then what you do is you start applying this to larger numbers of disks and larger numbers of spheres. But here is the punchline. The punchline, so what are you looking at here? So this is my packing fraction, so my disks shrink from right to left. These vertical lines, so to the left is where we expect the liquid to be, to the right is where we expect the solid to be. In between these lines is a two-phase region. So we expect there to be some kind of wild topology that's happening right here. So what we find is that if we do this and we look at this diffusion diameter, or we look at the mixing kind of diameter of the space, we find that these black locations, which are the locations of the largest discontinuous jump, appear right around where the last index one critical point is appearing. And that the location of that last index one critical point is slowly migrating to the right as we increase the number of disks. That's interesting. This actually becomes even more clear if we talk about the number of critical points as a function of packing fraction. So here we have large spheres. This is actually for spheres, and small spheres. And what I'm doing is I'm plotting cumulative distributions from the right for different numbers of different indices of critical points. And you see that we have this huge pileup right where we go from liquid to semi-liquid and solid. Remember the Betty numbers for the disks in an infinite strip. So this is for 9 spheres, and 10 spheres, and 11 spheres. And what you should be noticing is that these are getting steeper and more highly concentrated right around that location. And so that's it. We think that there's some topological catastrophe. We're trying to triangulate these spaces. We're trying to understand phase transitions as well as we can. And it feels like there's these kind of pseudo-random spaces there with really wild topology. And I hope that you might be interested in studying this too. That's it.
So, Jeremy, thanks a lot for this wonderful talk. And I think Jeremy proved enough that he's not only a material scientist, but a physicist and a mathematician as well. So I hope you agree. Yeah, questions?
Thank you very much for this interesting talk. Can you please explain a bit more the connection of the index of the critical points? What's happening, those discontinuity you mentioned in the index of one critical point that this kind of continuity happens.
Right. So this is not the first time that physicists have thought about it from this standpoint. And typically what they do is they talk about the index 0 ones as energy wells, or like kind of stable configurations. And they talk about the index 1s as saddle points, because that's the saddle point that they know about. And so they think about this in terms of connected components. Right, that we've got a connected component, we've got a connected component, and then I get a bridge, and then suddenly something happens. I think that that's not right. And I think really what we need to be doing is we need to be looking at the topology as a signature for these kind of singular geometries. And then what's actually relevant is how long it takes my system to explore the space. And if you take that viewpoint and you start thinking about, say, a 90-dimensional hypercube, and you think about the time that it takes you to go from one corner to the other corner, I can reduce this if I paste in that, the top cell. And then you start thinking about what these spaces look like. These are not hypercubes. They have these wild tendrils that go off in kind of off by themselves. And so it's very possible that if we put in a higher index critical point, it allows me to take the shortcut through the space that will dramatically reduce the diffusion distance. I suspect strongly that this is implicated in the transition between liquid and gas. But again, it's just a conjecture.
And sorry, does this index also helps you to have some predictions where this discontinuity happened?
We can't predict anything. This is just exploratory. If you can predict this, that might be a Nobel Prize. Right?
Okay, thank you.
Other questions? So you mentioned this is huge data sets, right?
Yes.
So for how long did you run these? For months or?
Well, if I'm thinking about processor hours, probably over a million. Well, yeah.
Jeremy, you mentioned in the beginning that
when you wrote down potential energy, people don't really believe that it's a pairwise function. You should be taking higher order interactions into account. So, but in your model, it's all built on pairwise.
It is not.
Oh, it's not.
No, I was just motivating. Just motivating. Nothing in our model assumes those interactions. That's why I went to the hard disks. Right? That was one of the very first things I did. I said, I'm going to simplify this by not making an explicit choice. I'm going to go to the hard disk potential as a way of stepping around that, because the idea is that the hard disk potential is somehow the core.
But isn't this a pair, like fundamentally pairwise interaction? There's a function F2 based on R. It has a funny shape. That's the hard disk part.
I guess.
And then your potential energy is just expressed as a sum of.
So effectively, all potentials that people actually use are based on the pairwise potential that I showed you in the previous one with perturbations.
I see. So there is never any higher order FT return.
Oh, there are absolutely, but they are small in magnitude relative to the F2, and that means that effectively all interactions are going to have this band around the diagonal where atoms are just allowed configuration.
I see. So the biggest point is that this is the most important topological feature. That's what we're going to capture in the function.
And the whole idea with topology is that it should be stable to these kinds of perturbations.
I see. So trying to introduce a model like this that actually also has higher returns.
Well, it absolutely makes sense if you're interested in simulating real materials, but I'm trying to boil it down to a math problem.
No, but of course, math problem does.
Right.
Right. One further? Well, then thanks, Jeremy, once again. And there are further talks coming up. But I think this is the last talk when we are all here in this auditorium. So let me take, therefore, the opportunity to thank the organizers and, well, 1, 2, 3 over there. So thanks so much for all the work that you put into this wonderful conference, like applying for grant funding and just running the whole thing. I think has been a lovely week, and it's not over yet because there are further talks to come. But yeah, just a heartfelt thanks to you all. And like with the talks before, I give over to other, maybe we start 5 minutes later to have a longer break. Well, certainly we deserve a coffee. So we are updating the schedule for the taxis and buses tomorrow. So please observe the piece of paper. It should be over there. Already I got an email that the taxi at 10:30 should be going a bit earlier because I need to catch the train. So if you are the 10:30 taxi, probably you will be leaving a bit earlier, 15 minutes. All right, so please observe the displays, and so we have a couple of parallel sessions. Just to, I'll try not to mess it up this time. So I think Rafa, there is a session with 3 talks and there is a session with 2 talks. So if I'm correct, the session with 2 talks is in the closer room, and the session with 3 talks is in the room which is farther away. I hope I got it right. There is no switch. There is no switch. Let's go get some coffee. Thank you.